Hello everyone, today we're going to talk about friction factor for turbulent flow. Let's see what is learning objective today for today's lecture. First, we're going to estimate friction factor for varying flow regime. And then we are going to understand how to use Moody's diagram. And third, we're going to apply the equation form for friction factor that we call that equation Holland equation. So to find friction factor, which we learned before, this is friction factor, there is two ways to do. One is Moody's diagram and the other one is equation. Okay, let's see how it works. So today we start with reviewing what we learned about Reynolds number and Darcy equation about head loss. Then again we review energy equation that we call Bernoulli's equation with correction factor. And then learn how to use Moody's diagram. Then we discuss equation for estimating F, which is very important. And then, as always, we solve some example. All right, let's see what we learned so far. So in this picture, you can see three different pictures. Maybe you can tell which one is laminar, which one is transitional, or which one is turbulent. But it's not a good idea to just look at the flow and tell which type of flow we have, because sometimes it's inside the pipe and we cannot see anything. That's why we learn about Reynolds number for internal flow. So Reynolds number depends on velocity. Always we talk about average velocity. It depends on the diameter and viscosity. Either it's kinetic viscosity or absolute viscosity. So density over absolute viscosity is kinetic viscosity, right? Then we learn about Darcy equation that is very good to find head loss. Head loss for Darcy equation depends on friction factor, the length of the pipe, the velocity of the flow, diameter of the pipe, and gravity. So it's easy to find the length, velocity, or diameter, but the most important thing is how to find friction factor. Do you remember from previous lecture how we can find friction factor for laminar flow? From previous lecture, you know if it's laminar, it's 64 over Reynolds number. So it's only when it's laminar flow. So when we have a laminar flow, it's very easy to find friction factor. But how about if it's transitional or turbulent? So today's lecture is about finding this friction factor when we have transitional or turbulent flow, which is important topic in designing piping system. All right, let's go over Bernoulli's equation or energy equation. General form is like this. So the first term, if you remember, is pressure head. The second one is velocity head. The third one is elevation head. Head for pump and head for head loss or head loss due to friction. Sometimes we have a turbine in the other side too. So you can see two new gases here, alpha 1 and alpha 2. This is something we're going to introduce today. We call them kinetic energy correction factor. If we have fully developed laminar flow, this correction factor is 2, whereas if it's turbulent flow, the correction factor is 1.05. So all the time when we write energy equation, you see we don't use alpha 1 and alpha 2 because we simply can assume almost always the flow is turbulent and alpha is almost 1. Okay, so if in the problem alpha is not given, just assume it's 1. And you know, most of engineering application in civil engineering, it's transitional or turbulent flow. All right, let's see how we can find friction factor for turbulent flow. We need to introduce two new important things and the terminology that we use. First, we know friction factor is function of Reynolds number and a relative roughness. This one called relative roughness. Epsilon called only roughness. All right, so we're going to introduce roughness shortly. Okay, in a second you will see what is roughness. So friction factor depends on Reynolds number and also relative roughness. Also depends on diameter. If it's a pipe, it's actual diameter. If it's a different shape, it's hydraulic diameter. There's two methods to find friction factor. One is equation form that I'm going to talk about it in a minute, and the other one is a graphical form that we call it Moody's diagram. Moody's diagram is an important diagram in fluid mechanics that a lot of civil engineering use it for a long time. It's a logarithmic equation. Okay, let's see what is absolute roughness and where we can find absolute roughness. Because we already know how to find Reynolds number, right? The only things that we need to know is the roughness. If we know these two, we can find friction factor either from equation form or graphical form. All right, let's find out what is roughness. The roughness, there is a table in your textbook that you can find the roughness. So if you look at this picture, this table, you can see, for example, for glass, the roughness is 0. And there is 2 units here, millimeter and feet, because the unit for roughness is length. All right, for example, for concrete, you can see roughness is 0.9, oops, it's 0.9 to 9 for concrete, depends on the aggregate we use in the concrete, it might be varied. Or for cast iron, you can see what is the roughness, or galvanized iron. A lot of piping system are either galvanized iron or cast iron, and sometimes they are commercial steel. So from here you can find epsilon or roughness. So how they find this absolute roughness? It's empirical number that they put some sand grain, they glue some sand grain in the pipe and then measure the friction factor based on that. So this is how we can find the roughness. Okay, so we know the roughness, we know it's easy to know relative roughness when we know absolute roughness. The other things was Reynolds number. We learned how to find Reynolds number. If we have 2 of these, we can find friction factor. Let's look at a big picture of Moody's diagram. that shows how we can find friction factor. In this graph, you can see the x-axis is a logarithmic chart, that the x-axis is Reynolds number, the y-axis is friction factor. Okay, so F is friction factor. All right. In the bottom one, you can see very smooth turbulent, and the top is fully rough turbulent flow. And over here, you can see different relative roughness. So first of all, we need to find Reynolds number. Then after we find Reynolds number, we can find relative roughness and then read friction factor. You can see a line here. It's for laminar flow. So you know, for laminar flow, friction is 64 over Reynolds number. And now you can see why it's laminar, right? Whereas for turbulent flow or transitional, it's a curve. So we don't have to use Moody's diagram for laminar flow because it's easier to find from this equation. But for turbulent and transitional flow, it's better to use the graph, the curve. All right, let's look at the real Moody's diagram. Here is the Moody's diagram, so it's a lot going on. That's why first I showed you a big picture of what we have in Moody's diagram. All right, so in x-axis you have Reynolds number. You have Reynolds number, and in the y-axis you have friction factor. Here you have relative roughness, or epsilon over d. Okay, so you can find relative roughness here, and then relative roughness here, and read Reynolds number from here, then just find out what is friction factor. You can see other things here. If you don't want to look at the table, for your textbook table for roughness, you can find roughness for different material here. For example, cast iron is 0.00085, or you know, some equation that we use to find out friction factor or continuity equation, it's written here. So it's very handy to use Moody's diagram. It's empirical and it's easy to use and find out what is friction factor. There is another equation that you can find friction factor, that's called Kullberg equation. So this is an empirical equation that it's good to find friction factor. So you can see friction factor here and here. Do you think it's easy to find friction factor from this equation? It might be a little bit hard to find friction factor because it's root square of f, both sides of equation, and then this f is inside logarithm, so it's not easy to find out. All right, but it's good between the Reynolds number between 4,000 and 10 to the power of 8, and it's a close fit compared to Moody's diagram. I think Moody's diagram is way easier to use and find friction factor compared to Kullberg equation. But this is one of the equations that might be useful to know. Or let's introduce another equation that is way easier than Kullberg equation. We call it Hallan equation. Halland equation, the only things that you need to know is to find friction factor is relative roughness again and Reynolds number. So my recommendation is either use Moody's diagram, finding Reynolds number and roughness to find friction factor, or use Halland equation. And Halland equation and Moody's diagram are different by within 2%. So you get very close answer from either Halland and Moody's diagram. So in an example, you can check both friction factor from the equation and from Moody's diagram. Some students prefer to use, Halland equation, and they use their calculator. It might be easier than find friction factor in Moody's diagram, but it's up to you which method you use. Both of them are fine. All right, so far we learned a lot of equation. Do we need all these equation? We learned about continuity equation. We learned about head loss, that in the head loss equation, this friction factor was so important to find. For laminar flow, it was 64 over Reynolds number, and for turbulent flow, we can find it either from Halland equation or Moody's diagram. Reynolds number was from previous lecture, you know how to find it, and this is how we can find friction factor. Okay, do we need all this equation? Yes. So it depends on what type of problem we have. So sometimes in the problem, the length is given, the diameter is given, the flow is given. We only want to know what is the pressure drop. Sometimes we know the length and diameter, and we know how much pressure drop we have in the system. We want to know how much flow we can get from this system piping system. And the other one is when we know the flow and the length and pressure drop, we are going to design diameter. What do you think about engineering problems? Usually in engineering problems, at the same time, we don't know the diameter, we just want to design a piping system. So you know from continuity equation, if you don't know diameter, it means you cannot find a velocity. Okay, so at the same time, we don't know both of them. How we can find such a problem? This is the topic for future lecture. If we don't know diameter, velocity, and flow rate, we need to use method of iteration. But for now, usually one of these are unknown, and we're going to find pressure drop or flow or design for the diameter of the pipe. So remember, we always need this equation to be able to solve this problem, any problem in internal flow. All right, as always, let's solve a practical example from internal flow and see how we can design this piping system, or we can find what is the head loss or pressure drop. All right. So this is the example that we have. Let's read it and see what is given and what we need to find. So a 6-inch diameter galvanized iron pipe transports water at 100 degrees Fahrenheit. So the diameter and materials for the pipe and the water temperature is given. Determine the head loss and the pressure drop in 200 feet of pipe if the flow is 400 gallons per minute. Okay, so the flow rate is given. The flow rate is given. We know the diameter, we know the length. What we need is head loss. What is the head loss? And what is the pressure drop due to this head loss? Okay, how to solve such a problem in internal flow? Let's just review what we have, what we need to convert. We need to be very careful about units and what we need to find and what is our assumption. So the diameter is given, so it's 6-inch diameter. So make sure you convert inch to feet. So 6/12 feet. The length is given. The flow is given gallon per minute. We need to convert it to cubic feet per second. So 1 minute is 60 seconds, right? And 1 feet cubic is 7.48 gallon. Okay, so this is a conversion for gallon per minute to cubic feet per second. Then the temperature is given from the table. From the table in your textbook, you can find what? The density and viscosity. So the density of water at 100 degree Fahrenheit, 100 degree, it was Fahrenheit, this one is Fahrenheit, is we are in British system, 1.927 a slug per feet cubic. And also we need absolute viscosity or kinetic viscosity because later on we want to find Reynolds number. So I use this, it's similar to V, its kinetic viscosity is 7.39 multiply 10 to negative 6 feet squared per second. Okay. So whenever the temperature is given, we can find the density, absolute viscosity, or kinetic viscosity. What else it's given? The material is given, it's galvanized iron. So you go to the table in your textbook, it's table 8.2, chapter 8. You can find out what is roughness. So it's 0.00.5 feet. Make sure you pick the one with the correct unit. If you're working with English system, you need to use the roughness that is in feet. If you use SI system, you need to find the roughness from the table that is in meter. So this is all we have and what we need to convert, and then what we need to find is head loss and pressure drop. There is two important assumptions. First of all, it's fully developed a steady flow, because if you remember the energy equation, it's one of the energy equation assumption. The other things, we always assume it in civil engineering, we work with incompressible flow. So this is all we have. Now we're going to find head loss. For head loss, if you remember, the equation depends on friction factor and also velocity. So it's good to find the velocity. Since I have a Q, I have the Q flow rate, I can find velocity from continuity equation, right? So from this equation, I can find velocity. All right, And then once we have Reynolds number, I have the roughness, I can find the friction factor either from Moody's diagram or from Halland equation. So first of all, let's find out what is velocity. All right, so V is Q over A. Velocity is 400 gallon per minute. Make sure you converted 1 minute multiply 1 feet cubic per 748 gallon divided by 60 seconds over area. Area is pi and the diameter was 3 inch, so divided by 12, it's feet squared. So from here you can find velocity. It's 4.5539 feet per second. All right, I have the velocity. Now it's easy to find Reynolds number. So Reynolds number is a velocity which is 4.539 multiply diameter. Diameter was 6 inch divided by 12. Make it feet. And the unit for this one, this is feet per second. Don't forget about unit. And it's 6 over 12 feet divided by kinetic viscosity, which is 7.39 multiply 10⁻⁶ feet squared over second. Let's see what is Reynolds number. Reynolds number is 0.7 multiply 10 to the power of 5. Anytime you find Reynolds number, make sure you know what type of flow it is. So we know if Reynolds number is smaller than 2300, it's laminar. But in this case, it's way greater than 2300. So it's laminar flow. It's turbulent flow. Okay. So from here, this is turbulent. Okay. Because sometimes it's laminar, we don't have to use Moody's diagram or Halland equation. If it's laminar, just we need to divide 64 by Reynolds number and we have the friction factor. So make sure it's turbulent flow. All right, so what is the next step? We know roughness, we know Reynolds number. If we know relative roughness, which is absolute roughness over D, and Reynolds number, we can find friction factor either from Halland equation or Moody's diagram. I'm going to use Halland equation to find out what is friction factor. All right. So let's see what is absolute roughness. So absolute roughness is epsilon. Okay. It's epsilon over D. What is epsilon was 0.005 feet divided by diameter, which is 0.5 feet. So absolute roughness, it's dimensionless, it's 0.001. Okay, I have absolute roughness, I have Reynolds number. Now I can find friction factor. All right, so 1 over friction factor root square is minus 1.8 logarithm of 0.001 over 3.7 to the power of 1.11 plus 6.9 over Reynolds number, which was 3.710 to the power of 5. All right, now 1 over root square of F is 6.98. From here, I use the calculator and find friction factor. Okay, friction factor is 0.0205. Friction factor is usually this very small number. Now you can compare with friction factor from Moody's diagram. Get something the same, maybe it's by 2% different, but you get almost 0.02 point, maybe 4 or maybe 3, but it's very close, but it doesn't affect the answer because it's very small number. All right, what's the next step? All we do, it's just finding friction factor to find the head loss. Now I have friction factor, length, diameter, velocity, and gravity. I can find the head loss. So let's substitute the number. Friction factor is 0.0205. It's dimensionless. Multiply, we have a 200 feet pipe over the diameter, which was 5 feet. Multiply the velocity, I found it from continuity equation, which is 4.539 feet per second. Don't forget about squared. I usually forget about squared here, over 2g, and make sure put the right gravity. It's British system, so it's 32.2 feet per squared second. So use your calculator and find head loss. Head loss is 2.66 feet. All right. Why we found head loss? Because in energy equation, we want to find the pressure drop, so we need to know what is head loss. So all the time we use Darcy equation, which is this one called Darcy equation. With energy equation together to solve the problem in internal flow. All right, after we find friction factor and find out what is head loss, the next step is to find the pressure drop. So for pressure drop, we're using energy equation. And the fun part of energy equation is to find out which one is 0. All right, so for this one, so they are in the same elevation, right? So if they are in the same elevation, Z1 is 0, Z2 is 0. We don't have any head loss. The only head loss we have is due to friction factor. What else is 0? We don't have any pump. What else is 0? V1 and V2 are not 0, but because they have the same size diameter and the flow is the same, from continuity equation, velocity at 1 equals velocity at 2, right? So I can cancel out these two. They're not 0. I just cancel them out. Now the only things I have is a P1, P2. I can find the pressure drop, right? And the head loss. Let's go ahead and just substitute everything we have. It's P1. Let me, change the color. It's P1 over gamma equals P2 over gamma plus head loss. So the pressure drop is from point 1 to point 2 is equals to head loss. What is head loss? Is 2.66 feet. We just find the pressure drop. But the equation for pressure drop is head loss multiply gamma. So we know the head loss. Head loss is 2.66 feet, okay? And gamma, or we can use, because we have the density, we can use head loss rho g. They are the same equation. So what is the density? It's 1.927 slug per cubic feet. We just found it from the back of textbook, from the table. What is gravity? Is 32.2 feet squared second. So we have everything. We can calculate the pressure drop, which is 16517. It's pound per squared feet. I want it to be in PSI, just I need to divide it by 144. So if I divide it by 114, I get it in PSI. So it's 1.15 pound per inch square or PSI. What does it mean? It means along 200 feet of pipe, we have about 1.15 psi drop in pressure. The most important things for us is pressure drop. So let's review what we learned today. We learned about friction factor in turbulent flow. To find friction factor, we need to use Holland equation or Moody's diagram. Once we have friction factor, we can find the head loss due to friction. Once we have head loss due to friction, from energy equation, we can find the pressure drop. And based on that, we can design the piping system. Sometimes we need a pump, or we need to come up with different strategy to design the piping system. Okay, so for next lecture, we're going to solve more complex problem for internal flow. Okay, let's call it a day and have a good rest of the day.